Tonight we're going to talk about something that sounds simple at first, the distance between stars. You've heard the numbers before, light years, billions of miles, vast incomprehensible distances, and most of us nod along, accept it, and move on. But here's the thing most people don't realise. The moment you actually stop and sit with those numbers, really sit with them, let them settle into your body the way cold air settles into a room, something shifts. Because the distance between stars is not just large. It is so far beyond anything your mind was built to understand that it changes the entire way you see the night sky. It changes the way you see yourself. And tonight, that is exactly what we are going to explore together. By the end of tonight, you're going to understand exactly why the universe, despite containing 400 billion stars in our galaxy alone, is for all practical purposes completely, terrifyingly empty. You're going to feel the weight of a single light year in a way no number has ever made you feel before. And you're going to look at the faint points of light above you with something new in your chest. Not just wonder, something quieter than that. Something closer to awe at the edge of vertigo. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Step outside on a clear night. Find a patch of sky away from the streetlights, away from the glow of your phone. Look up. What you see are points of light scattered across the darkness like dust on black velvet. They look close. They look almost reachable. Some of them seem to pulse gently as if they are breathing, and something in you, something very old and very human, feels a kind of comfort in that sight. The stars feel like company, like a ceiling overhead rather than an abyss beneath. But here is where I want to stop you. Here is where I want to sit with you for a moment, in the quiet, and ask you something. What if everything you feel when you look at those stars is a beautiful illusion? What if the sense of nearness, the sense of familiar company, is simply the result of a mind that was never built to understand what it is actually looking at? What if the truth, the real measured, mathematically verified truth, of what lies between you and the nearest star is so vast, so genuinely incomprehensible, that it borders on terrifying? Because that is exactly what we're going to discover tonight. Not in an abstract way, not with numbers that wash over you and disappear, but slowly, carefully, one step at a time. We're going to build a picture of the void between stars that you can actually feel, and I promise you, by the time we reach the end of this journey, the night sky will never look quite the same to you again. It will look more beautiful, yes, but also stranger, and in the best possible way, a little more honest. Let me start with something familiar, the sun. You know the sun. You feel it every morning on your skin. You understand it in a way you understand very few things in the universe, directly, physically, without any instrument or calculation. It is roughly 93 million miles from Earth. That sounds like a long way, and by any human standard it is. If you drove a car at 60 miles per hour without stopping, it would take you about 176 years to reach the sun, a lifetime and a half behind the wheel, never sleeping, never pausing, and you would still be inside our own solar system. You would not have even begun to approach the edge. Now hold that number in your mind. 93 million miles. That is one astronomical unit, 1 AU. The standard measuring stick astronomers use within our solar system. From the Sun to Earth, 1 AU. From the Sun to Mars, about 1.5 AU. From the Sun all the way out to Pluto, roughly 40 AU. So if you stacked 40 of those 93 million mile journeys end to end, you would reach the outer edge of the known solar system. That is already a distance so large it should give you pause, 40 times the distance from here to the Sun, and you're still inside the bubble of our own star's influence. And yet, the nearest star to our Sun, a small faint red dwarf called Proxima Centauri, is not 40 AU away. It is not 400 AU away. It is not even 4,000 AU away. It is approximately 268,000 AU from Earth. 268,000 times the distance from here to the Sun. Sit with that for a moment. Let that number breathe. Because what it means is that even the nearest star, the closest one, our immediate cosmic neighbour, is separated from us by a gulf so enormous that the entire span of our solar system, from the Sun to Pluto and back 40 times over, is nothing but a rounding error in comparison. This is the first thing I need you to understand tonight. The solar system, which already felt impossibly large, is essentially a dot, a single small dot, floating alone in the middle of a darkness so deep and so wide that crossing it, even at the speed of the fastest thing in the universe, takes more than 4 years. 4 years of travelling at 186,000 miles per second. Every second of every minute of every hour of every day for 4 full years. And at the end of that journey, you would arrive at a single dim star that you cannot even see with the naked eye from Earth. That is how far away the nearest star is. That is how alone we are, out here in this particular corner of the galaxy. Here is the thing most people don't realise when they look up at the night sky. Those points of light overhead, all of them, are not neighbours. They are not nearby. They are separated from each other and from us by distances so enormous that the word vast doesn't begin to cover it. The night sky gives you the impression of a ceiling studded with lights, all roughly the same distance away, like lanterns hanging in a dark room. But that is not what it is. What you are actually looking at is a 3-dimensional ocean of emptiness, stretching in every direction for incomprehensible distances, with individual stars scattered through it like single candles, separated by hundreds of miles of open water. Complete darkness between each one, complete, unbroken, almost perfect nothing. And this is the central mystery we're going to sit with tonight. Not just how far apart the stars are, though we will go deep into that, step by measured step, but what that emptiness actually means, what it tells us about the nature of the universe, about the possibility of life beyond our world, about the strange and fragile miracle of our own existence in this particular spot. Because the distance between stars is not just a fact of physics, it is the defining fact of our cosmic situation. It is the reason the universe is so quiet. It is the reason we have never heard from anyone else out there. It is the reason that for all the stars blazing across the sky, the space between them is the truest thing about the universe. Emptiness, silence, an ocean of nothing, stretching further than any mind was ever meant to reach. Tonight, we're going to cross that dark together, slowly, with our eyes open, one step at a time. And I think what you will find, what I hope you will find, is that the void between stars, far from being a cold and frightening thing, is one of the most profound and beautiful aspects of the cosmos. It is the canvas on which everything exists. It is the silence that makes the light meaningful. It is the space that gives each star its solitude, its singularity, its strange and ancient dignity. So settle in, let your body relax, let your breathing slow, because we have a long way to travel tonight, and the journey itself is the destination. There is a star out there that is, by cosmic standards, right next door. It is the closest star to our Sun, the closest point of light beyond our own solar system, and its name is Proxima Centauri. It sits at a distance of 4.24 light-years from Earth. That phrase gets used a lot in astronomy. 4.24 light-years. People hear it, nod, and move on. But tonight, I want us to stop at that number. I want us to actually open it up and look inside it, because what lives inside that number is one of the most quietly terrifying things I have ever encountered in all of science. Let's start with what a light-year actually is, because the word gets thrown around so casually that it has lost almost all of its meaning. A light-year is not a measure of time, it is a measure of distance. Specifically, it is the distance that light travels in 1 full year. And light, as you may know, is the fastest thing in the universe. Nothing moves faster. Light travels at approximately 186,000 miles per second. In a single second, a beam of light could circle the entire Earth 7.5 times. In 8 minutes and 20 seconds, it crosses the 93 million miles between the Sun and our planet. It is, by any human measure, incomprehensibly fast. Now take that speed, hold it in your mind, 186,000 miles every single second, without slowing, without pausing, without rest. And ask yourself, how far does something moving that fast travel in 1 full year? The answer is approximately 5.88 trillion miles. 5.88 trillion miles. That is 1 light year, a single light year, and Proxima Centauri is 4.24 of those away from us. which means the distance between our solar system and the nearest star is roughly 24.9 trillion miles, nearly 25 trillion miles of empty space, separating us from the closest point of light beyond our own sun. I want to give you an analogy, because numbers that large have a way of sliding off the mind without leaving a mark. Imagine you shrink the entire solar system down so that the distance from the Earth to the Sun, the 93 million mile journey, becomes just one single inch. 1 inch on a table in front of you. At that scale, Pluto, the distant outer edge of our solar system, sits about 40 inches away, a little over 3 feet. You could reach it with your arm, but Proxima Centauri at that same scale would be approximately 4.24 miles away. 4 miles! You would have to leave your house, walk through your neighbourhood, cross several city blocks, and keep walking for 4 miles before you reach the nearest star, and that tiny solar system you started with, that 3-foot stretch of planets, would be sitting on your kitchen table, invisible at that distance. Now think about that in the context of travel. Humans have launched objects into space. We have built rockets, probes, machines of extraordinary engineering that have escaped the gravity of Earth and sailed outward through the solar system. The fastest of these is Voyager 1, which launched in 1977 and has been travelling ever since. As of right now, Voyager 1 is moving at approximately 38,000 miles per hour. That is roughly 10 miles per second. To most people, that sounds impossibly fast, and by any earthly standard it is. A commercial airplane flies at about 570 miles per hour. Voyager 1 is moving at nearly 70 times that speed. It is the fastest object humanity has ever sent into space. And at that speed, how long would it take Voyager 1 to reach Proxima Centauri? The answer is approximately 73,000 years. 73,000 years of continuous travel at 10 miles per second before you arrived at the nearest star. To put that in human terms, 73,000 years ago, our ancestors were living in small hunter-gatherer groups, painting on cave walls and learning to survive the last ice age. Agriculture would not exist for another 60,000 years. Writing would not be invented for another 68,000 years. The entirety of recorded human history, every war, every empire, every discovery, every moment of beauty and horror and progress, fits inside the final 5,000 years of that journey. And Voyager 1, launched with all the ingenuity of the modern civilization, would still be travelling. This is what 4.24 light-years actually means, not a number, not an abstraction, a duration, a gulf. A silence so wide and so deep that our fastest machine would need longer than the full span of human civilization, multiplied many times over, just to cross it. And when I say that, I do not mean to make you feel hopeless. I mean to make you feel the weight of the cosmos, because there is something profoundly important about standing at the edge of what we can reach and looking honestly at how far it extends beyond us. And here is the detail that I find most quietly stunning of all. When you look up at the night sky and find the constellation Centaurus, low on the southern horizon for those of you in the northern hemisphere, you are looking in the direction of Proxima Centauri. The light entering your eye right now, if you were looking at it, left that star 4.24 years ago. You are not seeing the star as it is. You are seeing it as it was. 4 years in the past, that light began its journey across 25 trillion miles of empty space, crossing the void at the maximum speed the universe permits, and it ended that journey inside your eye, in your body, in this moment. That photon of light has been travelling since before you read this sentence, since before perhaps some small moment in your own life that you still carry with you. Proxima Centauri is a red dwarf star, small, dim, and cool by stellar standards. It burns at a fraction of the sun's brightness. If you replaced our sun with Proxima Centauri and kept Earth at the same distance, our sky would appear dim and reddish, like a permanent late afternoon in autumn. It is not a spectacular star. It does not blaze. It does not dominate. It simply sits there, quietly, 4.24 light-years away, the closest candle in an incomprehensibly large and dark room. And even it, even the nearest one, is so far from us that reaching it is beyond anything our civilization has yet built, or may build within any lifetime you or I will ever know. This is where our journey begins, not with a distant galaxy, not with the edge of the observable universe, just with the nearest star, one step, one neighbour, 4.24 light-years, and already the darkness between us is enough to take the breath away. When most people imagine the space between stars, they imagine something like a very dark room. Dark, yes. Cold, certainly. But a room still has walls, still has air, still has the faint presence of matter filling every corner. The darkness between stars is nothing like that. It is something far stranger, far more absolute, and far more difficult for the human mind to genuinely accept. Because the space between stars is not merely dark, it is, by almost every meaningful measure, nothing. And understanding what that word actually means, really means, at a physical level, is one of the most quietly unsettling things you can do on a calm night. Let us start with the air around you right now. The room you are in, wherever you are, is filled with air that you cannot see. That air is made of molecules, mostly nitrogen and oxygen, and those molecules are everywhere. In every cubic centimetre of air around your body right now, there are approximately 2.7 times 10 to the 19th molecules. That is 27 million trillion molecules in a space the size of a sugar cube. The air feels like nothing to you. It is invisible, weightless, unremarkable. And yet it is, by the standards of the universe, extraordinarily dense, extraordinarily full. It is practically a solid compared to what lies between the stars. In the interstellar medium, the technical name for the space between star systems, the average density of matter drops to somewhere between 1 and 10 atoms per cubic centimetre. Not molecules, atoms. Single, individual atoms drifting alone in the dark. 1 atom, perhaps 10, in the same cubic centimetre that contains 27 million trillion molecules in the air around you right now. The interstellar medium is, by any standard of comparison, essentially nothing. It is a vacuum so profound, so complete, that no laboratory on Earth has ever come close to replicating it. The best vacuum chambers humans have ever built still contain millions of molecules per cubic centimetre. The void between stars makes our finest laboratory vacuums look crowded. Here is an analogy that I find helps make this real. Imagine you took the entire Atlantic Ocean, all 310 million cubic kilometres of it, and you removed every single drop of water except for one. One solitary drop of water sitting somewhere in that vast empty basin. The space around that single drop, the almost incomprehensible emptiness of the dry ocean floor stretching in every direction, that begins to approximate the density of the interstellar medium. Not perfectly, not exactly, but it gives you a sense of the proportion. The space between stars is not a thin mist. It is not a sparse fog. It is a near-perfect absence of matter, broken only by the loneliest of particles drifting in an ocean of absolute nothing. And it is cold, brutally, almost unimaginably cold. The temperature of interstellar space in its quieter regions hovers around -270 degrees Celsius. To put that in context, the coldest temperature theoretically possible, absolute zero, the point at which all molecular motion stops entirely, is -273 degrees Celsius. Interstellar space is within 3 degrees of the coldest thing that physics says can exist, 3 degrees away from the absolute bottom of the temperature scale. When you step outside on a winter night and feel the cold biting at your skin, you're experiencing temperatures that are, cosmically speaking, almost tropical by comparison. Now, I want to be precise here, because the interstellar medium is not perfectly uniform. It has structure, it has regions. There are places where the gas is slightly denser, clouds of hydrogen that will eventually collapse under gravity and birth new stars. There are regions heated by nearby stars or the shock waves of stellar explosions, where temperatures spike to millions of degrees. There are filaments and bubbles and shells of gas shaped by forces acting over millions of years. The void between stars is not a featureless blank. It has texture in the way that an almost empty room might have a few dust motes drifting in a beam of light. But the dust motes do not change the essential nature of the room. The room is still empty, and the interstellar medium is still, in any sense that matters to a living creature, nothing. Here is the thing most people do not realize when they look up at the night sky. The stars look crowded from here. They look numerous, dense, scattered generously across the dark. On a clear night away from city lights, you might see 2,000 or 3,000 stars with the naked eye. And the temptation is to imagine that space, at a larger scale, is similarly populated. That the universe is full of stuff, full of matter, full of light, full of energy. But the opposite is true. The universe taken as a whole is almost perfectly empty. Matter, all the stars, all the planets, all the gas clouds, all the galaxies, makes up less than 5% of the total content of the universe. And even that 5% is spread so thinly across such an incomprehensible volume of space that the average density of the entire observable universe is roughly equivalent to a handful of atoms scattered across a volume the size of a large room. The universe is not full, it is almost entirely nothing. There is something deeply strange about sitting with that fact. We are creatures of density, of matter. We live on a rock surrounded by air, warmed by a star. Everything in our experience is built from the collision and interaction of particles. We have no instinct for emptiness on this scale. Our bodies were not shaped by evolution to understand a void that makes our finest laboratory vacuums look like soup. And yet here we are, orbiting a small star in a galaxy of 400 billion stars, separated from the nearest of those stars by more than 4 light-years of space, so empty it contains fewer atoms per cubic centimetre than the best vacuum we have ever manufactured. We are, in the most literal physical sense, alone in a vast and almost perfect nothing. But I want to leave you with something here, before we move on. The emptiness is not nothing in the sense of meaningless. It is not a void to be mourned. In a deep and strange way, the emptiness is what makes everything else possible. It is the space between the notes that makes music music. It is the silence between words that gives language its weight. The void between stars is what gives each star its solitude, its definition, its individuality. Without the darkness, the light would have no meaning. Without the emptiness, the matter would have no room to become anything at all. The universe is almost entirely empty, yes. And in that emptiness, somehow, against all odds, you exist. That is not a reason for despair. That is, if you let it be, one of the most astonishing things you will ever contemplate. I want to take you on a walk, not a long walk by human standards, a walk through the solar system, step by measured step, at a scale your body can actually inhabit. Because one of the reasons the distances between stars feel abstract is that we skip straight to the big numbers without ever building the foundation beneath them. We hear 4 light years, and we compare it to nothing, because we have nothing in our experience large enough to compare it to. So tonight, let us build the scale from the ground up. Let us feel each step before we take the next one. And I promise you, by the time we reach the end of this walk, the number 4.24 light years will no longer be an abstraction. It will be something you carry in your body. Let us begin right here. Earth, the planet you're lying on right now, curving gently beneath you in every direction. Earth has a diameter of roughly 7,900 miles. It is, by the standards of what we're about to explore, an almost invisibly small object. If you wanted to walk around the entire circumference of Earth at a comfortable pace, it would take you roughly a year and a half of walking without rest. That feels large. That feels like a meaningful distance. Hold that feeling, because it is about to become irrelevant. Now we step outward to the Moon, our nearest neighbour in space. The Moon orbits Earth at an average distance of about 239,000 miles. The Apollo missions covered that distance in roughly 3 days of travel. 3 days, moving at a speed no human had ever travelled before, to reach the closest object in space. If you shrank Earth down to the size of a basketball, the Moon at that scale would be a tennis ball sitting about 23 feet away. That already feels lonelier than most people imagine, not right next to each other. Separated. 2 objects in a room with empty space between them. From the Moon, we move to the Sun, 93 million miles from Earth. At the speed of the Apollo spacecraft, the journey would take roughly 4 months. If you drove a car at highway speed without ever stopping, you would arrive in about 176 years. The Sun is not close. It is not a neighbour in any human sense. It is a distant, blazing furnace that we orbit at a safe remove, connected to it only by gravity and light. On our basketball-scale model of Earth, the Sun would be a sphere roughly 9 feet across, about the size of a large beach ball, sitting approximately a third of a mile away from you. You would have to leave the building and walk several blocks to find it. Now we push further. Mars, at its farthest from Earth, sits about 250 million miles away. Jupiter, the giant of our solar system, orbits the Sun at roughly 5 times Earth's distance, about 500 million miles out. Saturn, with its extraordinary rings, sits at roughly 9 times Earth's distance from the Sun, Uranus at 19 times, Neptune at 30 times, and Pluto, small, cold and distant, orbits at an average of about 39 times Earth's distance from the Sun, nearly 3.7 billion miles from the star it circles. On our scale model, Pluto would be a tiny grain of sand sitting about 1/3 of a mile from the basketball that represents Earth, and more than 10 miles from the beach ball representing the Sun. Already, our solar system has become something that fills a small town, but we are not done, because the solar system does not end at Pluto. It ends, if we define its boundary as the edge of the Sun's gravitational influence, somewhere around 100,000 AU from the Sun. That is the outer edge of the Oort cloud, the vast spherical shell of icy objects that surrounds our solar system like a distant fog. 100,000 AU, 100,000 times the distance from Earth to the Sun. At our scale model, with the Sun as a beach ball, the outer edge of the solar system would be roughly 3,300 miles away, approximately the distance from New York to Los Angeles and back again. That is how large our solar system truly is when you count all of it. Not the planets we know, the full extent of the Sun's reach. And now we step outside. We leave the solar system entirely and we ask, how far to the nearest star? On our scale model, with Earth as a basketball, the Sun as a beach ball 1/3 of a mile away, and the solar system stretching thousands of miles in every direction, Proxima Centauri would sit approximately 100,000 miles away. 100,000 miles on a scale where Earth itself is the size of a basketball. The Moon in real life is only 239,000 miles from Earth. So on our model, the nearest star is less than half the actual distance to our own Moon, and yet it represents 4.24 light years, 25 trillion miles, of real, empty, absolute space. This is the moment where the scale breaks the mind. Not because the numbers are confusing, but because the numbers are clear. They are precise. They have been measured with extraordinary care by generations of astronomers using instruments of almost unimaginable sophistication. And what those numbers tell us is unambiguous. The solar system, which already felt impossibly vast, which already stretched to distances that would take a car 176 years just to begin to cross, is a single microscopic dot in the context of even the nearest interstellar distance. We are not a small planet in a large solar system. We are a small planet in a small solar system, sitting alone in the middle of an emptiness so profound that the distances within our own system are beneath notice. Here is what I want you to feel right now. Not despair, not smallness in the crushing sense, but something more specific, a kind of calibration, a gentle, honest recalibration of where you are and what surrounds you. Because most of us walk through our days with a vague sense that the universe is large, but a deeper, unexamined feeling that we are somehow near the middle of things, near the centre of a populated cosmos. The stars are out there, sure, but they are out there the way other cities are out there, distant but reachable in principle. What the scale tells us is something different. It tells us we're on an island, a small, warm, improbably fortunate island, surrounded in every direction by distances so vast and so empty that the journey between here and the nearest other island would consume more time than our entire civilization has existed. We are not near the centre of anything. We are alone, in the dark, on a rock, circling a modest star, in a corner of the galaxy that no one else, as far as we can tell, has ever visited. And the night sky, for all its beauty, is mostly just the darkness that surrounds us. Let us imagine for a moment that you decided to go, that you looked at the 4.24 light years between here and Proxima Centauri and you said, I want to cross that. I want to build something, launch it, and send it toward that faint red star. What would that actually take? Not in the vague, hand-waving way we sometimes talk about space travel, but concretely, physically, in terms of the real machines humanity has actually built and the real physics that govern how things move through space. Because when you work through the numbers, honestly, what you find is not just a technical challenge. What you find is something that reframes the entire human story in a single calculation. Let us start with Voyager 1, because it is the most honest answer we have to the question of how fast humans can currently travel through space. Voyager 1 launched on the 5th of September, 1977. It was designed to study the outer planets, Jupiter and Saturn, and then continue outward. It has been travelling ever since for nearly 5 decades without stopping, accelerated partly by the gravitational slingshot of the giant planets it passed. It is currently moving at approximately 38,000 miles per hour, 17 kilometers per second. By any earthly measure, that is extraordinary. A bullet from a rifle travels at roughly 1,800 miles per hour. Voyager 1 is moving at more than 20 times the speed of a bullet, continuously through the vacuum of space. At that speed, how long does it take to reach Proxima Centauri? The answer is approximately 73,000 years. 73,000 years of continuous travel at bullet times 20 speed before you arrive at the nearest star. I want you to sit with that number, the way you would sit with a stone dropped into still water, watching the ripples move outward. 73,000 years ago, anatomically modern humans were only just beginning to spread across the planet. The last ice age was underway. The sea levels were lower. Woolly mammoths walked the earth. Agriculture, writing, mathematics, philosophy, science, literature, none of it existed yet. None of it would exist for tens of thousands of years, and Voyager 1, launched with the full technological capacity of late 20th century civilization, would still be travelling through the dark when all of that history played out and more. But let us be generous. Let us imagine we built something faster, much faster. The fastest crewed spacecraft in history was Apollo 10, which reached a speed of approximately 25,000 miles per hour during its return from the Moon in 1969. Faster than Voyager 1's current speed, but only because of the gravitational pull of Earth it was falling toward. In deep interstellar space with no planets to slingshot around and no gravity well to fall into, sustained travel at even that speed would require continuous propulsion, fuel, engines, thrust, on a scale that staggers engineering. But let us say we managed it. At 25,000 miles per hour, the journey to Proxima Centauri would take approximately 114,000 years. Longer, not shorter, than Voyager 1, because Apollo 10's record speed was a brief peak, not sustained cruise. So let us dream bigger. Let us imagine a spacecraft travelling at 1% of the speed of light. That is 1% of 186,000 miles per second, still roughly 1,800 miles per second, or about 6.5 million miles per hour. No human technology today comes anywhere close to this. But let us imagine we achieved it. At 1% of the speed of light, the journey to Proxima Centauri would take approximately 424 years, 4 centuries of travel, longer than the United States has existed as a nation, longer than the interval between Shakespeare and today. A ship launched in the year 2025 would not arrive until roughly the year 2449. Everyone aboard at launch would be dead. Their children would be dead. Their grandchildren and great-grandchildren and great-great-grandchildren would be dead. The civilization that built the ship might be unrecognizable to the people who arrived. This is the concept of the generation ship. A vessel so large and so self-contained that it functions as a small world unto itself. People are born, live full lives, and die aboard the ship, with the mission passed from parent to child like a sacred inheritance across centuries. The idea has captured human imagination for decades. It appears in science fiction, in serious engineering proposals, in the quiet dreams of people who understand the distances involved and refuse to accept that they make the stars permanently unreachable. There is something deeply moving about the generation ship concept. It says that a civilization could commit to a journey that no individual will live to complete, that the act of beginning is itself enough, even if the ending belongs to people not yet born. But there are other ideas, more ambitious, more physically extreme. In the 1960s, a project called Orion proposed a spacecraft propelled by a series of nuclear explosions detonating behind a massive pusher plate. The mathematics suggested such a craft could reach speeds of several percent of the speed of light. It was never built. The Partial Nuclear Test Ban Treaty of 1963 effectively ended the project, but the physics was sound. More recently, the Breakthrough Starshot initiative, announced in 2016, proposed something even more radical. Tiny gram-scale spacecraft the size of postage stamps, accelerated to 20% of the speed of light by an array of ground-based lasers. At that speed, the journey to Proxima Centauri would take approximately 20 years. 20 years, within a human lifetime. The spacecraft would be too small to carry humans, but they could carry cameras, sensors, and transmitters, and the data they sent back, travelling at the speed of a light, would arrive roughly 4 years after they did. 20% of the speed of light. That sounds like the threshold where things become possible, and perhaps one day it is. But it requires a laser array with a combined power output greater than all the electricity currently generated by the entire human civilization. It requires materials that can survive acceleration forces tens of thousands of times the force of gravity. It requires a level of engineering ambition that makes every space mission in history look modest by comparison. It is not impossible, but it is not close. It is the kind of project that belongs not to this generation, or perhaps the next, but to some future version of humanity that has learned to think and build on timescales we currently cannot sustain. And this is what the distance between stars does to us, when we are honest about it. It does not crush ambition. It does not make the dream of reaching other stars feel foolish. It does something more interesting than that. It forces us to grow. It forces us to think, not just in years or decades, but in centuries and millennia. It forces us to ask what kind of civilization we want to be. One that plants seeds it will never see flower, or one that only invests in what it can harvest in a single lifetime. The stars are not close. They will not become close in our lifetimes, or our children's lifetimes. But the fact that we are already dreaming about how to reach them, already doing the mathematics, already building the first tentative proposals, says something extraordinary about the species that evolved on this small rock. We are, against all the odds of our brief and fragile existence, already reaching. There is something we've been assuming throughout this journey that I want to stop and examine. We've been talking about distances, vast, almost incomprehensible distances, as if they were simply a matter of space, as if the void between stars were just an enormous stretch of emptiness that, in principle, you could cross if you had enough time and enough fuel. But there is another dimension to these distances that changes everything. A dimension that is not about space at all. It is about time. And the key that unlocks it is the single most important speed in the universe, the speed of light. Light travels at approximately 186,000 miles per second. We have established that, but what we have not yet fully explored is what that speed means for the act of looking, for the act of seeing. Because when you look at something, you're not receiving information about that thing as it is right now. You're receiving light that left that thing some time ago and has been travelling toward your eyes ever since. For objects close to you, the delay is negligible. The light from your hand reaches your eyes in less than a billionth of a second. The light from a wall across the room takes a few nanoseconds. The light from the moon takes about 1.3 seconds. None of this is noticeable. None of this feels significant. But as the distances grow, the delay grows with them, and at interstellar distances the delay becomes something profound, something almost philosophical. When you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. The light entering your eyes right now left the surface of the sun before you sat down, before you turned off the lights, before perhaps some small and ordinary moment of your evening that has already passed into memory. If the sun were to suddenly vanish, simply disappear silently and completely, you would not know for 8 minutes and 20 seconds. You would sit in what felt like a normal evening, and then the light would stop. And only then would you understand that something 8 minutes ago, 93 million miles away, had gone terribly wrong. That 8-minute gap between event and knowledge is not a flaw in our instruments. It is a fundamental feature of the universe. Information cannot travel faster than light. Nothing can. Now take that principle and apply it to the stars. When you look at Proxima Centauri, you are seeing it as it was 4.24 years ago. The light reaching your eye tonight began its journey across 25 trillion miles of empty space more than 4 years in the past. Whatever Proxima Centauri looks like right now, in this moment as you breathe and the Earth turns beneath you, you cannot know. You will not be able to know for 4.24 more years. When the light carrying that information finally arrives, you're not looking at a star. You're looking at a memory of a star, a 4-year-old memory, preserved in photons, delivered to your eye across an incomprehensible distance. And as the distances grow, the look-back time grows with them. Sirius, the brightest star in the night sky, is approximately 8.6 light-years away. You're seeing it as it was 8.6 years ago. Betelgeuse, the famous red supergiant in the constellation Orion, is roughly 700 light-years away. The light you see when you look at Betelgeuse tonight left that star around the year 1325. The 100 Years' War between England and France had not yet begun. The Black Death was sweeping across Europe. No one on Earth in that moment could have imagined you, lying here, receiving the light their descendants would never live to see. And yet here it is, ancient light, still travelling, still arriving, still meaning something to a mind that was not yet born when it began its journey. The Andromeda Galaxy, the nearest large galaxy to our own, visible to the naked eye as a faint smudge in the northern sky, is approximately 2.5 million light-years away. The light you see when you look at Andromeda left that galaxy 2.5 million years ago. At that time, our ancestors were not yet fully human. They were early members of the genus Homo, or perhaps still Australopithecus, walking upright on the African savanna, using simple stone tools with brains roughly half the size of yours. Every star you can see in that smudge of light has had 2.5 million years to change since the moment that light departed. Some of those stars will have died. New ones will have formed. Planets will have completed hundreds of millions of orbits, and you are seeing none of that. You are seeing a snapshot, a fossil of light, 2.5 million years old, painting itself across your retina on an ordinary night. Here is the thing most people do not realize when they absorb this fact for the first time. It means the universe as we see it does not exist, not in the form we see it. The night sky is not a picture of the present. It is a collage of the past with every star and galaxy photographed at a different moment in history, layered on top of each other and presented to our eyes as a single simultaneous image. The nearby stars show us the recent past, years or decades ago. The more distant stars show us centuries or millennia ago. The farthest objects we can detect, quasars at the edges of the observable universe, show us the universe as it was nearly 13.8 billion years ago, when the cosmos was young and strange and almost unrecognizable. We are not looking out into space, we are looking back in time. Every direction you look is a different depth of history. And this produces a genuinely terrifying possibility that astronomers think about more than they perhaps let on. Some of the stars you can see tonight no longer exist. They have died, exploded as supernovae, collapsed into white dwarfs or neutron stars or black holes in the time it took their light to reach you. You are looking at ghosts. Beautiful, ancient, still luminous ghosts whose light has faithfully made its journey across the void, only to announce the existence of something that has since ceased to be. You cannot know which ones. You cannot tell a living star from a dead one by sight alone when the light takes centuries to arrive. The night sky, for all its permanence and comfort, is populated by an unknown number of objects that are no longer there. I find this idea both deeply unsettling and deeply beautiful in equal measure. Unsettling because it means our picture of the universe is always out of date, always incomplete, always a reconstruction of a past that we cannot fully verify. Beautiful because it means that light is, in a sense, a form of memory. Every photon that reaches your eye has carried its information faithfully across distances and timescales that dwarf anything human civilization has ever produced. The light from a star that died 1,000 years ago is still out there, still travelling, still carrying its message. The universe does not forget easily. It keeps its records in light, and those records travel forever, long after the things that made them are gone. Look up at the night sky and find a star. Any star. Pick one that catches your eye. Perhaps one of the bright ones in Orion, or the steady blue-white point of Sirius in the south, or a faint unnamed point near the edge of your vision. Hold it in your attention for a moment. Your eye places it exactly, with the same quiet confidence it places a candle across a room or a lamp at the end of a hallway. The star is there, fixed, certain, occupying a precise and knowable point in the darkness above you, and here is what I need you to understand tonight. It is not where it appears to be. It has not been there for a very long time. What you're pointing at is not a location in space, it is a location in the past. Stars are not nailed to a fixed backdrop. They are not decorations hung on a velvet ceiling. They are enormous spheres of burning plasma, each one moving through space on its own trajectory, orbiting the centre of the galaxy the way planets orbit a star. Our own sun moves at approximately 140 miles per second as it sweeps through its vast galactic orbit. The stars around us are doing exactly the same, moving, drifting, carving slow and immense arcs through the Milky Way over millions of years. None of them are standing still, none of them are waiting. And because light takes time to travel, The position you see for any given star is not its current position. It is the position that star occupied at the moment its light departed, years, decades, centuries, or millennia ago, depending on the distance. Let us make this concrete. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light you see when you look at Sirius tonight left that star 8.6 years ago. In those 8.6 years, Sirius has continued moving through space. It has travelled an enormous distance from the point where it was when that light departed. The Sirius that exists right now, in this precise moment, as you breathe and the Earth rotates beneath you, is not in the location your eye is reporting. It has moved on, and for more distant stars the discrepancy grows proportionally. A star 600 light-years away is seen at the position it occupied 6 centuries ago, while its current location has drifted silently onward, unknown to us, unreachable by any observation we can currently make. Astronomers call this apparent drift proper motion, the measurable change in a star's position across the sky over time, caused by its actual movement through space combined with the changing angle of our perspective. Most stars move so slowly across our line of sight that the shift is imperceptible across a human lifetime without instruments. But Barnard's star, a dim red dwarf about 6 light-years away, has the fastest proper motion of any star visible from Earth. It creeps across the sky at a rate that would carry it the apparent width of the full moon in roughly 180 years. In 10,000 years it will have drifted noticeably away from where we see it now, and because it is only 6 light-years distant, what we observe is a relatively recent snapshot, only 6 years out of date. For stars hundreds of light-years away, the drift we observe is based on positions that are medieval, or ancient, or older still. Now consider the constellations themselves, those familiar patterns that humans have been naming and navigating by for tens of thousands of years. Orion, the Big Dipper, Cassiopeia, Scorpius. These shapes feel permanent, as ancient and fixed as the concept of the sky itself, but they are in the most literal sense temporary. The stars that form each constellation are not physically grouped together. They are scattered at vastly different distances, each one at a different depth in space, each one seen at a different moment in the past, their light arriving at Earth from wildly different points in history. The pattern you see is a projection, a flat shadow cast by a 3-dimensional arrangement of unrelated stars, assembled by your eye into a shape that exists only from your particular vantage point. From a different star system, even a nearby one, Orion would be unrecognizable. Its stars would fall in entirely different patterns against an entirely different backdrop. The constellations are not things in the universe. They are things in the human mind, born from a specific view at a specific moment in cosmic time, and those patterns are changing. Over thousands of years, the proper motions of the individual stars that make up each constellation will carry them apart, dissolving the familiar shapes into new arrangements that our distant descendants will name and mythologize as if they had always been there. The Big Dipper, recognizable to almost every culture in the Northern Hemisphere, will look noticeably different in 50,000 years. In 100,000 years it will be unrecognizable. The sky is not a fixed painting, it is a slow film, playing at a speed far beneath the threshold of human perception, but playing nonetheless. Here is the detail that I find most quietly haunting of all. Some of the stars you see tonight may already be dead, not metaphorically, literally. A star 600 light-years away that exploded 500 years ago is still visible to you right now as a calm and steady point of light. The light from its explosion has not yet arrived. It is racing toward us at 186,000 miles per second, still a century away from reaching Earth, while the light from before the explosion continues to paint the star as alive and burning in your sky. You have no way of knowing. You cannot tell a living star from a dead one when the light takes centuries to arrive. The sky you see is populated by an unknown number of ghosts, stars that no longer exist, still sending their ancient light faithfully onward, still arriving, still registering as present in a sky that is actually a museum of the past. Betelgeuse, the famous red supergiant in the shoulder of Orion, roughly 700 light-years away, is one of the most discussed candidates for this kind of invisible death. Astronomers have long known it is nearing the end of its life, though they debate the timeline. It could explode in 10,000 years, or 100,000, or perhaps far sooner than either estimate. But here is the thing, it may have already exploded. If Betelgeuse went supernova 600 years ago, we would not yet know. The light from that explosion would still be travelling toward us, centuries away from arrival, and in the meantime, we would continue to see it as it was before the event, dim and red and steady in Orion's shoulder, alive in our sky while its actual remains drift and cool in the dark 700 light-years away. I sit with this idea often, and I find it does something interesting to the way the night sky feels. It makes it feel less like a ceiling and more like a depth, less like a backdrop and more like an ocean, with things at different distances and different ages, all sending their signals simultaneously toward a small blue planet, where creatures with eyes briefly appear and look up and try to make sense of what they see. The stars are not where they appear. They are not when they appear, but the light is real and ancient, and it has crossed distances that humble every human achievement to reach you here, in this quiet moment, at the end of this long and ordinary day. We have been walking carefully, step by step, from the familiar to the extreme, from the distance to the moon, to the sun, to the edge of our solar system, to the nearest star. And at each step the distances have grown by factors that strain the imagination. But now I want to zoom out further, much further. I want to pull back until our entire solar system, that vast 3 billion mile span of planets and asteroids and comets, and the thin reach of the sun's gravity, becomes a single invisible point. I want to show you the full scale of the Milky Way galaxy, because when you see it whole, when you hold its true dimensions in your mind, what you discover is something that should not be possible, and yet is undeniably, measurably, mathematically true. A galaxy of 400 billion stars is, for all practical purposes, empty. The Milky Way is a barred spiral galaxy, a slowly rotating pinwheel of stars, gas, dust, and dark matter, with long curving arms trailing outward from a dense central bar. It is approximately 100,000 light-years across. Let that settle for a moment. 100,000 light-years. We established that a single light-year is roughly 5.88 trillion miles. 100,000 of those laid end to end gives you the diameter of our galaxy. If you travelled at the speed of a light, the fastest speed the universe permits, from one edge of the Milky Way to the other, the journey would take 100,000 years. Not 100,000 miles per hour, 100,000 years at the speed of light. The Milky Way is not large in the way that a mountain is large, or an ocean is large, or even a planet is large. It is large in a way that belongs to an entirely different category of existence. And within that 100,000 light-year span, there are approximately 400 billion stars. 400 billion individual suns, ranging from dim red dwarfs barely large enough to sustain nuclear fusion, to blue supergiant monsters hundreds of times the mass of our own sun, burning with a fury that will consume them in only a few million years. 400 billion. If you counted one star per second without stopping, it would take you roughly 12,700 years to count them all. More than twice the length of recorded human history just to count the stars in our single galaxy. And our galaxy is not even a particularly large one. The universe contains an estimated 2 trillion galaxies, each with their own hundreds of billions of stars. The numbers are at some point beyond meaningful comprehension. They become something you feel rather than think. But here is the extraordinary thing. Here is the fact that stops me every time I return to it. Despite containing 400 billion stars, the Milky Way is overwhelmingly, almost perfectly empty. The average distance between stars in our galaxy, not at the sparse outer edges but on average, across the whole structure, is approximately 4 to 5 light-years. 4 to 5 light-years of empty space between each star and its nearest neighbour, on average, throughout the entire galaxy. The same kind of distance we have spent several chapters trying to fully grasp. That terrifying Voyager needs 73,000 years gulf. That is the typical spacing, not the exception, the rule. Let me give you the analogy that I think captures this better than any number can. Imagine you could shrink the entire Milky Way down to the size of Europe. The whole galaxy, 100,000 light-years across, compressed until it fits across the width of a continent. At that scale, each individual star would be roughly the size of a single grain of sand. Not a marble, not a pebble, a grain of sand. And those grains of sand, those 400 billion of them, would be separated from each other by an average distance of several kilometers. several kilometers of empty space between each grain of sand scattered across a continent. If you stood in the middle of that model galaxy, you would be surrounded in every direction by an almost featureless plain. You would have to walk for kilometers before encountering the next grain. The space between them would be, to your eyes, indistinguishable from nothing. This is what the Milky Way actually is. Not a crowded city of stars shoulder to shoulder, blazing at close range. A wilderness, an almost unbroken wilderness of void, with occasional solitary points of light separated by gulfs that take light itself years to cross. The image most of us carry of our galaxy, perhaps drawn from photographs of other spiral galaxies, those gorgeous sweeping pinwheels of light, is deeply misleading. Those photographs make galaxies look dense, luminous, almost solid with starlight. But that impression is an artifact of photography and human vision, which integrate the faint light of billions of distant stars into a collective glow. Individually, those stars are invisible at such distances. The glow is an illusion of density. The reality is separation. The reality is silence. Our Sun sits in one of the Milky Way's spiral arms, the Orion arm, sometimes called the local arm, about 26,000 light-years from the galactic centre. We are not in the crowded core, where stars are packed somewhat more tightly and the density of matter is higher. We're in the suburbs, in a quiet, relatively sparse stretch of one of the outer arms, orbiting the galactic centre at roughly 140 miles per second, completing one full orbit approximately every 225 million years. The last time our solar system was in this same position in its galactic orbit, the dinosaurs had not yet appeared on Earth. Before that, the first complex multicellular life was only beginning to evolve. The galaxy turns slowly, and we are passengers on a journey so vast and so gradual that no civilization in human history has witnessed even the tiniest fraction of it. And yet, even here in the suburbs, the emptiness is the defining characteristic of our neighbourhood. The nearest star system to our own, the Alpha Centauri system, containing Proxima Centauri and two slightly larger companions, is 4.24 light-years away. The next nearest Barnard star is about 6 light-years. After that, a handful of others within 10 light-years. In our local stellar neighbourhood, a sphere of space 10 light-years in radius centred on our Sun, there are only a handful of star systems. A handful. In a sphere with a radius of nearly 60 trillion miles. The local universe is not a neighbourhood in any human sense of warmth and proximity. It is an expanse of near-nothingness, with isolated points of heat and light separated by cold and dark distances that make all of human experience look like a footnote. I want to leave this chapter with something that I think is worth carrying into sleep tonight. The galaxy is not crowded. The universe is not crowded. The dominant substance of both, measured by volume, is nothing. And we are here anyway, on this small, warm, improbably fertile rock, circling a modest star in a quiet arm of an ordinary galaxy, in the middle of an emptiness so vast and so complete that the mere fact of our existence is, by any reasonable measure, extraordinary. We did not arise in a rich and populated cosmos. We arose in a wilderness, in a silence, in a void that stretches in every direction further than any mind was ever meant to reach. And somehow, against all of that, here you are, breathing, thinking, looking up. We have established the distances. We have felt the scale, walked through the emptiness, and sat with the almost perfect void that separates star from star across the Milky Way. But I have not yet asked the question that, to me, sits beneath all the others. Why? Why are the stars so far apart? Why did the universe arrange itself this way, spreading its matter so thinly, spacing its light so widely, leaving so much of everything as nothing? The answer lives in the physics of how stars are born, and when you understand that process, the loneliness of stars starts to feel not like an accident, but like an inevitability, like the only outcome a universe like ours was ever going to produce. Stars are born from clouds, specifically from vast, cold clouds of hydrogen gas and dust called nebulae, which drift through the interstellar medium in enormous diffuse masses. These clouds are not small. A typical star-forming nebula might span dozens or even hundreds of light-years, vast enough to contain the raw material for hundreds or thousands of new stars. For most of a nebula's existence, it simply drifts. It is too diffuse, too spread out for gravity to get a grip. The gas is cold and slow and the individual atoms within it are separated by distances large enough that their mutual gravitational attraction is negligible. The cloud is, in its natural state, content to remain a cloud. But something can disturb that equilibrium, a shock wave from a nearby supernova, the gravitational ripple of a passing star, the compression caused by the spiral arms of the galaxy sweeping through like a slow wave. Whatever the trigger, the effect is the same. A region of the cloud becomes slightly denser than its surroundings, and once a region is slightly denser, gravity begins to work. The denser region pulls surrounding gas inward. As it pulls, it grows denser still. As it grows denser, it pulls harder. A feedback loop begins, slow at first, then accelerating, as gravity compounds upon itself over hundreds of thousands of years. The cloud begins to collapse, falling inward under its own weight, fragmenting as it goes into smaller and smaller clumps, each clump collapsing in turn toward its own centre. At the heart of each collapsing clump, the gas compresses and heats. The atoms, previously drifting in near-perfect cold and isolation, are now being pressed together by the weight of everything above them. The temperature rises, the pressure builds, and after perhaps 100,000 years of collapse, the core of the clump reaches a temperature of approximately 10 million degrees Celsius. At that point, something extraordinary happens. The hydrogen atom, specifically their nuclei, the protons at their centres, are moving so fast and are pressed so tightly together that they begin to collide with enough force to fuse. Two protons slam together and stick, releasing an enormous burst of energy in the process. Nuclear fusion ignites, and a star is born. But notice what this process produces. Not a continuous sheet of stellar material spread evenly across space, not a dense fog of half-formed stars pressing against each other. Discrete objects, individual, separate, gravitationally bound spheres of plasma, each one isolated from its neighbours by the vast distances that separated the collapsing clumps of gas before they fell inward. The stars inherit the spacing of the cloud, and the cloud was always thin, always vastly more empty than full, always a whisper of matter distributed across distances that dwarf the objects it eventually produces. The stars are born alone because the raw material of their birth was always alone, scattered thinly across a universe that made no provision for closeness. And once formed, stars do not drift together. They do not seek each other out. The gravity of an individual star is real and powerful, but it falls off with the square of distance, meaning that at the separations typical between stars, the gravitational pull of one star on its neighbour is almost unmeasurably small. Our Sun and Proxima Centauri, 4.24 light-years apart, exert a gravitational influence on each other that is so faint it has essentially no effect on either one's orbit around the galaxy. They are strangers in the gravitational sense. They pass through the same galactic neighbourhood over millions of years without meaningfully interacting, ships on an ocean so vast that proximity is never more than relative. There are exceptions. Some stars form in binary or multiple systems, two or more stars gravitationally bound to each other, orbiting a common centre of mass. In fact, it is estimated that roughly half of all Sun-like stars exist in binary or multiple systems. Alpha Centauri, our nearest stellar neighbour, is actually a triple system. Two Sun-like stars, Alpha Centauri A and Alpha Centauri B, orbiting each other relatively closely, with Proxima Centauri potentially bound to them at a much greater distance. These stellar families form from the same collapsing cloud, fragments of the same original clump of gas that never fully separated before fusion ignited. They are twins, or triplets, born together and gravitationally bound from the moment of their formation. But even binary stars are separated from each other by distances that, on human scales, are enormous, and they are separated from all other star systems by the same interstellar gulfs that separate every other star from its neighbours. The interstellar medium, the thin gas and dust that fills the space between stars, is the material left over after star formation. Not everything in a nebula collapses into stars. Much of it remains dispersed, too spread out and too lacking in density for gravity to gather it. This leftover material drifts between the stars in a state of extraordinary thinness, occasionally compressed by stellar winds or supernova shockwaves into new dense regions that may, millions of years later, seed another generation of star formation. The universe recycles its material slowly, over timescales that make geological time look brief. A hydrogen atom in the interstellar medium today might spend 1 billion years drifting in the cold before it finds itself inside a collapsing nebula, on its way to becoming part of a new star. The cosmos is patient in a way that is genuinely difficult for creatures who measure their lives in decades to absorb. What strikes me most about all of this is that the loneliness of stars is not incidental. It is structural. It is built into the physics of gravity, the thermodynamics of gas clouds, the mathematics of how matter collapses under its own weight. A universe with the physical laws this one has was always going to produce widely spaced, isolated stars separated by years of light travel time. The emptiness between them is not a gap waiting to be filled. It is the natural and permanent state of a cosmos where gravity acts locally, and space is simply overwhelmingly vast. We look up at the stars and feel their distance as a kind of longing, a yearning across the dark toward other lights. And perhaps that longing is itself a kind of answer. We are the universe's way of noticing its own solitude. We are the only things, as far as we know, that look at the spaces between the stars and feel something about them. And that feeling, quiet, ancient, real, is not nothing. In a universe this empty, it might be everything. Here is a question that I suspect has occurred to you at some point, perhaps on a clear night when the sky felt particularly full and alive. With 400 billion stars moving through the Milky Way, all of them orbiting the galactic centre, all of them in constant motion, sweeping through space at tens of miles per second. Why do they not collide? At those numbers, at those speeds, the galaxy seems like it should be a slow-motion catastrophe. A churning sea of near misses and violent impacts, stars smashing into each other across billions of years of continuous motion. And yet the night sky is calm. The stars are steady. The galaxy turns without apparent disaster. The answer to why is one of the most clarifying demonstrations of cosmic emptiness you will ever encounter, and it is, in its own quiet way, completely shocking. Let us start with the numbers. The Milky Way is approximately 100,000 light-years in diameter, and perhaps 1,000 light-years thick at our location in the disk. Within that volume, there are roughly 400 billion stars. 400 billion sounds like an almost impossibly large number, and in human terms, it is. But the volume of the Milky Way's disk is also almost impossibly large. When you divide the number of stars by the volume of space they occupy, the result is an average density of approximately 1 star per 300 cubic light-years. 1 star in a cube of space, 300 light-years on each side. To visualize that, a cube 300 light-years on a side contains on average a single star. 1 point of light, 1 burning sphere of plasma, surrounded in every direction by an unbroken expanse of essentially nothing. Now think about what this means for the probability of collision. 2 stars moving through this density of space are like 2 grains of sand dropped from opposite sides of a continent, falling through the air at random angles. The continent is not empty, it has other grains of sand scattered across it. But the grains are so small, and the continent is so large that the probability of any 2 of them colliding is extraordinarily, almost laughably small. Stars have physical diameters measured in hundreds of thousands of miles. Our Sun is roughly 865,000 miles across. That sounds large. In human terms, it is almost incomprehensibly large. But compared to the distances between stars, measured in trillions of miles, the physical size of a star is so negligible that stars are, for the purposes of collision mathematics, essentially points, dimensionless dots in a space so vast that their physical extent is beneath notice. Here is the analogy that makes this visceral for me. Imagine you are standing in the middle of an empty field that stretches as far as you can see in every direction, say 100 miles across. In that entire 100-mile field there are 2 grains of sand, just 2. Both of them are moving slowly, drifting in random directions. What is the probability that those 2 grains of sand collide? You already feel the answer intuitively. It is vanishingly small. The field is simply too large, and the grains are simply too tiny for a collision to be anything other than an extraordinary accident. Now scale that up to the distances between stars and multiply the field by a factor of trillions, and you begin to approach the actual mathematics. Stellar collisions within a galaxy are not common. They are not even rare in the ordinary sense of the word. They are events of almost unimaginable improbability, requiring a specific and unusual set of conditions to occur at all. and yet they do occasionally happen. In the densely packed cores of globular clusters, ancient spherical collections of hundreds of thousands of stars orbiting outside the main disk of the Milky Way, the stellar density is high enough that collisions and near misses become genuinely possible over billions of years. Astronomers have found evidence of what are called blue straggler stars in globular clusters, stars that appear younger and hotter than they should be, given the age of the cluster. The leading explanation is that they formed from the collision or merger of two older stars, which combined their mass and essentially rejuvenated, burning hotter and brighter than either parent. These stellar mergers are not violent explosions in the way you might imagine. They are slow, gravitationally guided processes, playing out over thousands of years as two stars spiral gradually inward toward each other. Cosmic collisions happen in slow motion. But what about entire galaxies? Galaxies do collide. This is well established and well observed. The Milky Way itself is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbour, currently approaching us at roughly 70 miles per second. In approximately 4.5 billion years, the two galaxies will begin to merge, a process that will take hundreds of millions of years to complete, a slow and gravitational dance that will reshape both structures into something new. This is not a secret. It is one of the most well-known facts in modern cosmology, and it raises an obvious and slightly alarming question. When two galaxies containing hundreds of billions of stars each collide and merge, what happens to all those stars? The answer is deeply strange and deeply revealing about the nature of cosmic emptiness. Almost nothing happens to them. They pass through each other like ghosts. The stars of the Milky Way and the stars of Andromeda will interpenetrate over hundreds of millions of years, the two galaxies tumbling through each other under their mutual gravity, and the individual stars will almost certainly never collide. The distances between stars within each galaxy are simply too enormous. The stars will be gravitationally stirred, their orbits disrupted and scrambled, their positions within the merged galaxy rearranged over millions of years. The gas clouds within each galaxy, however, will collide. Gas is diffuse and spread across vast regions, and when gas clouds meet, they compress and heat and trigger enormous waves of new star formation. The collision of two galaxies is, paradoxically, one of the most spectacular acts of creation in the universe. New stars ignite by the billions in the compressed gas of the merger. But the existing stars themselves drift through each other untouched, separated by the same vast distances that have always protected them. This is the arithmetic of collision, and it is simultaneously reassuring and humbling. Reassuring because it tells us that our Sun and its planets are in no imminent danger from passing stars. The nearest stellar neighbour is 4 light-years away, and the mathematics of their relative motions make a direct collision essentially impossible on any timescale relevant to human civilization. Humbling because it reminds us, once again, that the defining characteristic of this universe is not fullness but emptiness, not collision but avoidance, not proximity but distance. We live in a cosmos where 400 billion stars share a single galaxy and barely notice each other, where two entire galaxies can pass through each other like smoke through smoke, their stars never touching. The universe is not a crowded place. It is the loneliest place imaginable, and somehow, in the middle of all that loneliness, here we are. We have been talking about the space between stars as if it were simply nothing, as if the void were a pure and featureless blank, absolute zero of substance stretching between the isolated islands of stellar light. And in one sense, as we established early in our journey, that is true. The density of matter between stars is so low that it makes our finest laboratory vacuums look dense by comparison. A few atoms per cubic centimetre, drifting in cold and darkness. But here is what I have not yet told you. The space between stars is not nothing. It is something. Something thin and strange and vast. Something that connects every star in the galaxy to every other in a web of extraordinary subtlety. Astronomers call it the interstellar medium, and once you know it exists, once you understand what it actually is, the void between the stars feels less like an absence and more like an ocean. The interstellar medium is the collective name for all the gas, dust, plasma, magnetic fields, cosmic rays, and faint radiation that fills the space between star systems throughout the galaxy. It is not uniform. It has structure, texture, regions of varying density and temperature and composition, shaped over billions of years by the births and deaths of stars, the shockwaves of supernova, the slow gravitational tides of the galaxy's rotation, and the relentless pressure of starlight pushing outward in every direction. To call it simply empty space is like calling the ocean simply wet. Technically accurate, but missing almost everything that matters about what it actually is and what it does. The most abundant component of the interstellar medium is hydrogen, the simplest and most ancient element in the universe, the raw material from which the first stars formed 13.8 billion years ago and from which stars are still forming today. Most of this hydrogen exists in one of three forms, depending on the temperature and density of its local environment. In the coldest, densest regions, the molecular clouds where star formation occurs, hydrogen exists as molecules, two atoms bonded together, mixed with traces of carbon monoxide, water ice, and thousands of other complex molecules that form on the surfaces of dust grains in the cold dark. In warmer, less dense regions, the hydrogen exists as individual neutral atoms, drifting separately through space. And in the hottest regions, near young massive stars or in the aftermath of supernova explosions, the hydrogen is ionized, stripped of its electron by intense radiation or heat, reduced to bare protons swimming in a thin, searingly hot plasma. These three phases of the interstellar medium coexist throughout the galaxy, interleaved and interacting, constantly exchanging matter and energy across the boundaries between them. A molecular cloud collapses and forms new stars. Those stars pour out ultraviolet radiation that ionizes the surrounding gas, carving glowing bubbles of plasma called Chi regions, among the most visually spectacular objects in the universe, if you could see them with your own eyes. The most massive of those stars burn hot and fast and die in supernovae, blasting shockwaves outward at thousands of miles per second, compressing the surrounding medium into thin shells of dense gas that sweep through the galaxy like ripples on a pond. Those shells eventually slow, cool and fragment, seeding new molecular clouds with the heavy elements forged in the dead star's core. The interstellar medium is not static. It breathes, it cycles, it remembers every star that has ever lived and died within it. And then there is the dust. Interstellar dust is one of the most consequential substances in the galaxy, despite the fact that it represents only about 1% of the mass of the interstellar medium. Interstellar dust grains are tiny, typically between a fraction of a micrometer and a few micrometers across, smaller than the wavelength of visible light. They are composed of silicates, carbon compounds, iron and ice, built up atom by atom in the cold outer atmospheres of dying stars and scattered through space by stellar winds and supernova explosions. These tiny grains absorb and scatter starlight, blocking our view through the densest parts of the galaxy and making the central bulge of the Milky Way invisible to ordinary optical telescopes. They also provide surfaces on which complex molecules can form, including remarkably some of the organic molecules that are the chemical precursors of life. The interstellar medium does not merely connect stars. In a very real sense, it prepares the raw materials from which living things are eventually built. The magnetic field threaded through the interstellar medium is another of its hidden wonders. The galaxy is permeated by a weak but pervasive magnetic field, generated by the motion of charged particles through the interstellar plasma and wound and stretched by the galaxy's rotation over billions of years. This field is extraordinarily faint, millions of times weaker than the Earth's magnetic field, but it acts across such vast distances that its influence on the structure and behavior of the interstellar medium is profound. It shapes the way gas clouds collapse, influences the paths of cosmic rays, and helps organize the spiral structure of the galaxy itself. The interstellar medium is not just matter and radiation. It is threaded through with invisible lines of force that extend across thousands of light years, tying the gas and dust of the galaxy into a coherent dynamic structure. Cosmic rays are perhaps the most surprising inhabitants of the interstellar medium. These are not rays in the sense of light or radiation, despite the name. They are particles, protons, atomic nuclei, and electrons, moving through the interstellar medium at nearly the speed of light, accelerated to extraordinary energies by supernova shockwaves and other violent processes. Cosmic rays permeate the galaxy, passing through the interstellar medium in all directions, and they pass through you right now, several per second, as they have for the entirety of your life. The interstellar medium is not a barrier to them, it is a highway. They travel through it unimpeded, carrying energy from one part of the galaxy to another, ionizing the gas they pass through, influencing the chemistry of molecular clouds, and delivering a faint but constant reminder that the void between stars is never truly at rest. And then there are the nebulae, those places where the interstellar medium becomes briefly, magnificently visible, where a dying star illuminates the gas around it, or where a dense cloud glows with the reflected light of nearby stars, or where the shockwave of a supernova has compressed and heated the surrounding medium into glowing filaments of plasma. The Orion Nebula, visible to the naked eye as the fuzzy middle star in Orion's sword, is an active stellar nursery roughly 1,300 light-years away, a region of dense molecular cloud lit from within by the fierce ultraviolet radiation of newly formed massive stars. The Crab Nebula in the constellation Taurus is the expanding remnant of a supernova observed by astronomers in the year 1054, a shell of glowing gas still rushing outward, nearly 1,000 years after the explosion that created it. These nebulae are the moments when the interstellar medium steps out of invisibility and shows us what it actually is. Not empty space, but a living, cycling, ancient ocean of matter and energy that connects every star in the galaxy to every other, silently across the dark. On the 5th of September, 1977, a small spacecraft the size of a compact car was launched from Cape Canaveral into the Florida sky. It weighed roughly 825 kilograms. It carried a suite of scientific instruments, a nuclear power source, a radio transmitter, and something else. Something added almost as an afterthought, but which has since become one of the most poignant objects ever made by human hands, a 12-inch gold-plated copper disc encoded with sounds and images from Earth, music, greetings in 55 languages, the sound of rain, of wind, of surf, of a mother's first words to a newborn child, a record intended for no specific recipient, launched into a void so vast that the probability of it ever being found is almost indistinguishable from zero. And yet someone put it there anyway. That decision alone tells you something important about the kind of creatures we are. The spacecraft was Voyager 1. Its twin, Voyager 2, had launched 16 days earlier on a slightly different trajectory. Both were designed primarily to study the outer planets, Jupiter, Saturn, Uranus, and Neptune, using a rare alignment of the giant planets that occurs only once every 175 years to slingshot from one to the next in a single continuous journey. The mission was an extraordinary success. Voyager 1 sent back the first detailed images of Jupiter's swirling storms and volcanic moon Io in 1979. It revealed Saturn's rings in breathtaking clarity in 1980, and then it kept going. Long after its primary mission was complete, long after its cameras were turned off to conserve power, Voyager 1 kept travelling outward, deeper into the solar system, deeper toward the threshold between the Sun's domain and the true interstellar ocean beyond. For decades, scientists watched Voyager 1's progress with a particular question in mind. Where exactly does the solar system end and interstellar space begin? The boundary is not a visible line. It is a physical transition, the point where the solar wind, the constant stream of charged particles blowing outward from the Sun in all directions, finally loses enough energy that it can no longer push back against the thin gas of the interstellar medium. This boundary is called the heliopause. It is the outermost edge of the heliosphere, the vast bubble of solar influence that surrounds our star and everything that orbits it. Crossing the heliopause means crossing from the Sun's territory into the territory of the galaxy itself. It means entering the interstellar medium. It means, in the most literal physical sense, leaving home. For years, scientists debated whether Voyager 1 had crossed the heliopause. The data was ambiguous, the instruments were aging, the signals travelling at the speed of light took over 17 hours to reach Earth by the time the crossing was expected. Then, in 2012, the evidence became undeniable. The density of the particles surrounding Voyager 1 changed sharply. The direction of the local magnetic field shifted. The flux of cosmic rays from outside the solar system increased dramatically. Every instrument that could still function agreed. Voyager 1 had crossed the heliopause. It had entered interstellar space. For the first time in history, a human-made object was travelling through the medium between the stars. The moment was quiet, as great moments often are. No explosion, no visible boundary, just a change in numbers on a readout, transmitted by a faltering radio signal across more than 11 billion miles of empty space. As of now, Voyager 1 is the most distant human-made object in existence. It is currently more than 15 billion miles from the Sun, moving outward at roughly 38,000 miles per hour, deeper into the interstellar medium with every passing second. The signal it sends back, still faintly detectable by the largest radio telescopes on Earth, takes more than 22 hours to reach us at the speed of light. Voyager 1 is powered by the decay of plutonium, and its power supply is slowly fading. Sometime in the late 2020s, it will no longer have enough power to operate any of its scientific instruments. Its transmitter will fall silent, and then it will simply drift. A small metal object moving at 38,000 miles per hour through the interstellar medium, silent and dark, carrying its golden record into a silence so deep and so permanent that it is genuinely difficult to think about without feeling something in your chest. What is Voyager 1 detecting out there, in the interstellar medium beyond the heliopause? The instruments still functioning have painted a picture of a region that is, true to everything we have established, almost unimaginably thin and cold. The density of particles outside the heliopause is slightly higher than inside, compressed by the ram pressure of the interstellar medium pushing against the solar wind. The magnetic field is oriented differently, aligned with the galactic magnetic field rather than the Sun's. Cosmic rays from supernovae and other violent galactic events flood in from all directions without the partial shielding provided by the heliosphere. Out there, beyond the bubble of our star's influence, the interstellar ocean is real and measurable, and exactly as sparse and cold and ancient as the physics predicted. And yet Voyager 1 is not even close to leaving the solar system in the full sense of the word. The heliopause marks the edge of the heliosphere, but the solar system's gravitational reach extends far beyond that. The Oort cloud, that vast distant shell of icy objects, extends perhaps a quarter of the way to the nearest star, to distances of 50,000 or even 100,000 AU from the Sun. Voyager 1, at roughly 160 AU from the Sun, has barely scratched the surface of this outer region. To cross the Oort cloud entirely and enter what you might call truly interstellar space, gravitationally speaking, would take Voyager 1 approximately 300 years at its current speed, and to reach Proxima Centauri, as we established early in our journey, would take approximately 73,000 years. There is something about Voyager 1 that I find more moving the longer I think about it. It is not the technology, extraordinary as that is. It is not the scientific data, invaluable as that has been. It is the simple fact of its existence out there, right now, tonight, as you lie here in the dark. A small machine made by human hands is drifting through the ocean between the stars. It carries a golden record with the sounds of rain and music and a mother's voice. Its builders are gone. Its mission controllers are aging. The civilization that built it has changed beyond recognition since it was launched. And it travels on regardless, silent and faithful, carrying its tiny message into a void so vast that the message may never be received. Voyager 1 is the furthest thing from you that has ever been touched by a human hand, and it is still, by cosmic standards, right next door. Let us sit with a question that has haunted human beings for as long as we have understood what the stars actually are. If the galaxy contains 400 billion stars, and if even a small fraction of those stars have planets, and if even a small fraction of those planets have conditions suitable for life, and if even a fraction of that fraction have produced intelligent beings capable of looking up and wondering, then where is everybody? The universe should be full of voices, full of signals, full of evidence that we're not alone in this extraordinary and improbable experiment called consciousness. And yet, we have heard nothing. No radio transmissions, no laser pulses, no engineered structures visible in the data from our telescopes, no signals of any kind that cannot be explained by natural processes. The sky is silent, and the silence, when you measure it against the scale of what should be out there, is one of the most terrifying things in all of science. This is the Fermi paradox, named for the physicist Enrico Fermi, who is said to have raised the question in a casual lunchtime conversation in 1950. The paradox is not a technical puzzle with a clean solution. It is a confrontation between two sets of facts that appear to be irreconcilable. On one side, the vast age and size of the galaxy, the enormous number of stars and planets, the relative simplicity of the chemistry that produces life on Earth, and the fact that given enough time, a technologically advanced civilization should be able to spread across the galaxy. On the other side, complete unbroken silence. No signals, no visitors, no megastructures, nothing. The paradox is not that we have found no life, it is that we have found no evidence of life, anywhere, despite a universe that seems statistically obligated to produce it in enormous quantities. And here, at the heart of the Fermi paradox, the distances between stars reassert themselves with quiet force, because even if the galaxy is full of civilizations, even if intelligent life arose on thousands or millions of worlds over the last several billion years, the interstellar distances we have spent this entire journey exploring may be sufficient all by themselves to explain the silence. Consider the mathematics of communication. A radio signal sent from Earth today travels at the speed of light. It reaches Proxima Centauri in 4.24 years. A civilization there, if one existed, could detect it, compose a reply, and send that reply back to us. The round-trip time for a single exchange, 8.48 years, nearly a decade to complete one question and answer. Across the width of the galaxy, 100,000 light-years, a single exchange would take 200,000 years. 200,000 years of waiting between question and answer. In the entire span of recorded human history, which covers roughly 5,000 years, we could not have completed even a tiny fraction of one galactic-scale conversation. This is not merely an inconvenience, it is a structural barrier. Human civilizations have risen and fallen, languages have been born and died, entire ways of life have appeared and vanished, within timescales far shorter than the time required for a signal to cross even a modest fraction of the galaxy. If a civilization on the other side of the Milky Way sent us a greeting signal when the Roman Empire was at its height, that signal would not arrive for another 98,000 years. And if we replied the moment it arrived, our reply would not reach them until long after our sun has begun its expansion toward a red giant. The galaxy is not just large, it is so large that communication across it operates on timescales that are, by any measure relevant to a biological civilization, essentially eternal. But perhaps communication is not the right frame. Perhaps an advanced civilization would not send signals. Perhaps it would send ships, or probes, or some form of self-replicating machine that could spread from star to star, making copies of itself at each destination and continuing outward in an expanding wave. This is the concept behind the idea of a von Neumann probe, a self-replicating spacecraft that could, in theory, explore the entire galaxy in a relatively short cosmological timeframe. Even at a speed of 1% of the speed of light, far beyond anything we can currently build, such probes could cross the galaxy in about 10 million years. 10 million years sounds long. But the Milky Way is roughly 10 billion years old. If any civilization in our galaxy had launched such probes even 1 billion years ago, they would have had time to visit every star in the galaxy 900 times over. And yet we find no evidence of them. No probes, no messages left in our solar system, no signs that anyone has ever been here. This is where the paradox deepens into something genuinely unsettling. The absence of evidence is not proof of absence. That much is true. But the absence of evidence at this scale, sustained across decades of increasingly sensitive searching, is not nothing. It is a data point. A heavy, persistent, difficult to explain data point. And the explanations that have been offered over the years are, almost without exception, either deeply sobering or deeply strange. Perhaps intelligent life is extraordinarily rare, so rare that we are in fact the only civilization in the galaxy, or one of only a handful. Perhaps civilizations reliably destroy themselves before they develop the capacity for interstellar communication or travel. Perhaps the distances are simply too great, and every civilization that has ever existed has lived and died in isolation, separated from all others by gulfs of space and time that no signal and no ship has ever crossed. Perhaps there is something about the nature of advanced intelligence that inevitably leads it away from the kind of detectable activity we are looking for. Inward rather than outward, quiet rather than loud. Or perhaps, and this is the possibility I find most quietly haunting, perhaps they are out there, and the distances are the answer. Perhaps the universe is full of islands of consciousness, each one separated from all the others by light years of empty space, each one looking outward into the dark and finding only silence, each one wondering the same question we're wondering right now, not because life is rare, not because civilizations destroy themselves, but simply because the void between the stars is so unimaginably vast, and the speed of light so finite, and the timescales of cosmic distance so far beyond the span of any biological life, that the galaxy's civilizations are like fireflies in a continent-sized field at night, each one glowing, each one alive, each one utterly unaware of all the others, separated by distances that their light will never quite cross in time. I find something both terrifying and strangely comforting in that image. Terrifying because it suggests that the silence around us may be permanent, that we may live out the entirety of our civilization's existence without ever receiving confirmation that we are not alone. Comforting because it does not require that we are alone. It only requires that the universe is large, and that light is slow, and that the distances between stars are exactly as extraordinary as everything we have explored tonight. The silence is not an answer. It is a question, still open, still waiting, drifting outward from every radio telescope we have ever pointed at the sky, travelling at the speed of light towards stars that will not receive it for years or decades or centuries. We're calling out into a darkness we cannot see the end of, and we are listening. And the listening itself, patient, persistent, quietly hopeful, is one of the most beautiful things our species has ever done. There is a particular kind of human being who looks at an impossible distance and does not feel defeated, who looks at 73,000 years of travel time and thinks, then we need a faster ship, who looks at the 4.24 light years between here and Proxima Centauri and begins, quietly and seriously, to do the mathematics of crossing it. These people are not dreamers in the idle sense. They are engineers and physicists and aerospace scientists who have spent careers working at the boundary between what exists and what might exist, who understand the constraints of the universe well enough to know where the doors are, even if those doors are not yet open. Tonight I want to spend some time with their ideas, not because any of them will be built tomorrow, or perhaps even in our lifetimes, but because the act of imagining how to cross the void says something profound about who we are as a species and what we might one day become. The most straightforward approach to interstellar travel, in concept if not in engineering, is simply to go slowly and accept the time. This is the generation ship, a vessel large enough and self-sufficient enough to function as a world unto itself, carrying not a crew but a civilization, people who live full lives aboard, raise children, grow old and die, and pass the mission on to their descendants across centuries or millennia. The generation ship does not require any physics beyond what we already understand. It does not need exotic propulsion or new science. It needs engineering on a scale we have never attempted, a closed-loop life support system capable of sustaining thousands of people for hundreds of years, a structural integrity to survive the rigors of deep space, and a social architecture capable of maintaining purpose and cohesion across generations that will never see the destination their ancestors chose for them. The generation ship is a test not of physics, but of civilization, of whether a human community can hold together across timescales that dwarf the entire span of any nation in history. But most serious proposals for interstellar travel today focus on speed rather than patience, on closing the distance faster rather than simply enduring it longer. And the most promising class of ideas involves not rockets, but light. The concept of a light sail, a spacecraft propelled not by burning fuel, but by the pressure of photons striking a reflective surface, has existed in theoretical form since the early 20th century. Within our solar system, light sails are a practical and already tested technology. Several spacecraft have used solar radiation pressure for propulsion, and the Planetary Society's Light Sail too successfully demonstrated controlled solar sailing in Earth orbit in 2019. But solar sailing has a fundamental limitation. The pressure of sunlight falls off rapidly with distance from the sun, becoming too faint to be useful beyond the inner solar system. The breakthrough idea behind Breakthrough Starshot, the initiative announced in 2016 by a group of scientists and investors, including the late Stephen Hawking, is to replace the sun with a laser, an enormous ground-based laser array, generating a combined power output of roughly 100 gigawatts, focused on a sail only a few meters across, but only a few hundred atoms thick, attached to a spacecraft, a star chip, that weighs only a few grams. The laser fires for a few minutes, accelerating the tiny craft to roughly 20% of the speed of light. At that speed, the journey to Proxima Centauri takes approximately 20 years. The starship arrives, gathers data with its onboard sensors, and transmits its findings back to Earth at the speed of light, a signal that arrives 4.24 years after transmission. The total mission time from launch to first data, roughly 25 years, within a human lifetime, possibly within the lifetime of someone alive today. The engineering challenges are, to put it mildly, significant. A sail only a few hundred atoms thick must survive acceleration forces tens of thousands of times the force of gravity during the laser burn. The laser array must be pointed with extraordinary precision across a distance that grows from 0 to millions of miles in a matter of minutes. The starship must survive 2 decades of travel through the interstellar medium, where even a single dust grain, at 20% of the speed of light, carries enough energy to destroy it on impact. The onboard electronics must function without repair or replacement for 20 years in conditions of extreme radiation and cold. And the data the starship sends back, from 4 light-years away, using a transmitter with the power of a small flashlight, must be detectable by the most sensitive radio telescopes on Earth. None of these problems are unsolvable in principle. All of them are, in their current state, unsolved. There are other ideas, wilder and more speculative but no less seriously discussed in the scientific literature. Nuclear pulse propulsion, the concept behind Project Orion in the 1960s, would use a series of controlled nuclear explosions to push a spacecraft forward, potentially reaching several percent of the speed of light. The Bussard ramjet, proposed in 1960 by physicist Robert Bussard, imagined a spacecraft that scooped interstellar hydrogen as it travelled, using it as fuel in a continuous fusion reaction, a ship that would accelerate as long as it flew, potentially approaching relativistic speeds. Antimatter propulsion, in which the annihilation of matter and antimatter releases energy with 100% efficiency, would be the most powerful rocket fuel physically possible, if we could ever manufacture and contain antimatter in useful quantities, which currently we cannot. And then there are the ideas that venture beyond conventional physics entirely. Warp drives, wormholes, the manipulation of space-time itself, concepts that remain for now in the realm of mathematics rather than engineering, but which are taken seriously enough that real physicists spend real careers examining whether they are possible in principle. What strikes me about all of these ideas is not their current feasibility, or lack of it. What strikes me is the persistence behind them. The fact that human beings, confronted with distances that should by rights inspire only despair, instead respond with calculation, with proposal, with the quiet, stubborn refusal to accept that the stars are simply beyond reach. We are a species that evolved on a single small planet, that learned to fly only about 120 years ago, that first left Earth's atmosphere less than 70 years ago, that has so far sent only one object beyond the boundary of our solar system. And we are already designing, however tentatively, the tools that might one day carry us to another star. The timeline is uncertain, the obstacles are real and serious, but the direction of travel is clear. I think about the people who will be alive when, or if, a starship reaches Proxima Centauri and sends back its first data. They will receive a signal from 4 light-years away, generated by a machine the size of a postage stamp built by a civilization that no longer quite resembles the one that launched it. And in that signal, however faint, will be the first direct sensory data ever gathered from another star system. The first photons ever measured from the surface of a world that is not our own solar system, transmitted across the void between the stars by something human hands made and human minds designed. That moment, whenever it comes, if it comes, will be one of the great turning points in the history of our species, not because it will end the loneliness of the distances, but because it will prove, finally and irrevocably, that the distances can be crossed. Everything we have explored tonight has been built on a single quiet assumption, that the distances between stars, vast as they are at least fixed, that the void is large but stable, that the 4.24 light-years between here and Proxima Centauri is a number you could write down and trust to remain true tomorrow and next year and 1,000 years from now. And for our immediate stellar neighbourhood, that assumption is close enough to accurate. The stars near us are moving relative to each other, but slowly, on timescales of millions of years. For any practical human purpose, the local distances are stable. But when we zoom out, when we look not at the distances between individual stars, but at the distances between galaxies, and then between galaxy clusters, and then across the full observable universe, something extraordinary and deeply unsettling comes into view. The universe is not static. It is expanding, and not just expanding, accelerating. The darkness between things is growing right now in every direction, faster and faster with every passing moment, and the long-term consequences of that acceleration are, by any honest measure, among the most terrifying facts in all of cosmology. The expansion of the universe was first discovered observationally by the astronomer Edwin Hubble in 1929. Hubble was studying the light from distant galaxies and noticed a pattern. The light from almost every galaxy was shifted toward the red end of the spectrum. This redshift, analogous to the way a siren drops in pitch as it moves away from you, indicated that the galaxies were moving away from us. Not just a few of them, almost all of them. And the further away a galaxy was, the faster it was receding. This was the observational signature of an expanding universe. Not galaxies moving through space away from some central point, but space itself stretching. The fabric of the cosmos growing larger, carrying the galaxies with it the way raisins in a rising loaf of bread are carried apart not by their own motion, but by the expansion of the dough between them. There is no center to this expansion. Every point in the universe sees every other point moving away from it. We're not at the middle of anything. The expansion is everywhere, simultaneously, at all scales. For most of the 20th century, cosmologists assumed the expansion was slowing down. Gravity, after all, acts as a brake. The mutual attraction of all the matter in the universe should, over time, gradually decelerate the outward motion. The question was whether there was enough matter to eventually halt the expansion entirely and reverse it into a final collapse, the Big Crunch, or whether the expansion would slow but continue forever in a gradual and eternal drift. The answer, revealed in 1998 by two independent teams of astronomers studying the brightness of distant supernovae, was neither of these. The expansion is not slowing down, it is speeding up. The universe is not decelerating under the pull of gravity. It is accelerating, expanding faster and faster with every passing year, driven by a mysterious energy that fills all of space and that nobody fully understands. Astronomers call it dark energy, and it constitutes approximately 68% of the total energy content of the universe. It is everywhere, it is dominant, and it is winning. The implications of this acceleration are profound and in the very long term, almost incomprehensible in their desolation. Right now, the expansion of the universe is noticeable only at cosmological scales, between galaxy clusters separated by hundreds of millions of light years. Within our local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller satellite galaxies, gravity is strong enough to hold the group together against the expansion. The distances within our local group are not growing. We are gravitationally bound to our neighbours. But beyond the local group, the expansion is already carrying other galaxy clusters away from us at extraordinary speeds. Galaxies at a distance of roughly 14 billion light-years are receding from us at the speed of light. Beyond that threshold, called the Hubble horizon, galaxies are receding faster than light. Not because they are moving through space faster than light, which relativity forbids, but because the space between us and them is expanding fast enough that the net rate of increase in distance exceeds the speed of light. The light from those galaxies can never reach us. They are already, in a meaningful sense, gone. And as the universe continues to accelerate, that horizon draws closer. More and more galaxies cross the threshold of irreversible recession, their light redshifting to lower and lower frequencies, their signals growing fainter and fainter, until they pass beyond the edge of what can ever be observed from here. In 1 trillion years, an almost inconceivable span of time, 100 times the current age of the universe, the local group will be an island in a void so vast and so dark that no trace of any other galaxy will be visible. The billions of galaxies we can see today in our most powerful telescopes will have receded beyond detection. A civilization that arose 1 trillion years from now, in what remains of our galaxy, would have no observational evidence that any other galaxies had ever existed. They would look out at a perfectly dark sky beyond the local group and see nothing. they would have no way of knowing that the universe had ever been filled with the light of 2 trillion galaxies. The evidence will be gone, swept away by the expanding darkness. I find this idea almost too large to hold. We exist in what cosmologists call the cosmic window, a brief period in the history of the universe when the galaxies are close enough to observe, when the evidence of the Big Bang is still visible in the cosmic microwave background radiation, when the structure of the universe is still legible to those who know how to read it. We are, in a genuine sense, fortunate to exist now rather than in the deep future, when the universe will have become a darker, emptier, and far less comprehensible place. The universe is not eternal in the sense of being forever observable, forever rich with structure and information. It is slowly erasing itself. The expansion is not just separating galaxies, it is, on the longest timescales, eliminating the possibility of knowledge about what once existed. And here, at the edge of this vast and sobering picture, I want to return to something close and small and immediate. The distance between you and the nearest star is 4.24 light-years. That is the distance we began with, on this long night's journey. It has not changed. It will not change significantly in your lifetime, or in the lifetime of anyone you will ever know. The expansion of the universe operates on scales so far beyond the human that it is, for any practical purpose, irrelevant to the life you are living. The stars above you are still there. The light is still crossing the void. Proxima Centauri is still burning, 4 light-years away, sending its faint red glow across the dark toward a small blue world that has barely begun to understand the scale of the place it inhabits. The expanding darkness is real. It is coming, in the deep future, on timescales that make all of human history irrelevant. But it is not here yet, and tonight, the stars are still within reach of your imagination, which is the furthest and most extraordinary reach any of us will ever have. We have travelled a long way tonight, from the familiar comfort of a clear sky seen from a backyard or a window, or a quiet patch of ground somewhere on this small and improbable planet, through the distances that separate us from the moon and the sun and the outer reaches of our solar system, past the threshold of the heliopause, where Voyager 1 drifts in silence through the interstellar medium, across the 4.24 light-years to the nearest star, a gulf that would consume 73,000 years of our fastest travel. Through the vast and almost empty structure of the Milky Way, 400 billion stars separated by an average of several light-years of nothing. Past the collision mathematics that showed us 2 galaxies can merge like smoke through smoke without their stars ever touching. Through the interstellar medium, that thin and ancient ocean of gas and dust and magnetic fields and cosmic rays that connects every star in the galaxy in a web of extraordinary subtlety. And finally to the edge of the observable universe, where dark energy is pulling the galaxies apart and the darkness is deepening with every passing year. We have covered an enormous amount of ground, and I want to end where we began, not with the vastness, but with the light. Here is the thing I keep coming back to, the thing that seems to me to matter more than any of the numbers we have examined tonight. The light crosses the void, despite everything, despite the distances that break the mind, despite the emptiness that makes our finest vacuums look like soup, despite the cold that sits within 3 degrees of absolute zero, despite the expanding darkness that will eventually swallow every galaxy beyond our local group. The light still crosses the void. Right now, tonight, photons that left Proxima Centauri 4.24 years ago are arriving at Earth. Photons that left Sirius 8.6 years ago are arriving at Earth. Photons that left the Andromeda Galaxy 2.5 million years ago are arriving at Earth. All of it travelling at 186,000 miles per second, across distances that dwarf every human achievement, every human timescale, every human concept of large, and arriving here, at this small blue world, at your eye, in this moment. The universe has been sending its light toward you for your entire life, and for billions of years before you were born, and it has never once stopped. Think about what a photon of starlight actually is. It is a quantum of electromagnetic energy, a particle with no mass and no charge, travelling at the maximum speed the universe permits, carrying information about the temperature and composition and motion of the star that emitted it. It left its source as the result of an atomic process inside a star. an electron dropping to a lower energy state, releasing its excess energy as a single particle of light. That particle travelled outward in all directions, or rather countless identical particles did, spreading in a sphere that grew larger by the speed of light in every direction. The vast majority of those photons crossed the void and hit nothing, passing between galaxies, between stars, between planets, through the near-perfect emptiness of space forever, never interacting with another particle, never arriving anywhere. But some of them, an infinitesimally small fraction, travelled in exactly the right direction to cross the specific distance to this specific planet, and enter the atmosphere and pass through the lens of a human eye, and strike a rod or cone cell on the retina, and trigger a nerve impulse that travelled to a brain and became, in that brain, the experience of seeing a star. The probability of any given photon making that journey and ending in that way is so small it barely exists, and yet it happens millions of times a second every time you look at the night sky. You are, in the most literal physical sense, made of light that has crossed the void, not metaphorically. The energy that drives the chemistry of your body comes ultimately from the sun, from photons that crossed 93 million miles of space and were absorbed by plants and converted into the molecules that built every cell in your body. The calcium in your bones was forged in the nuclear furnace of a star that died billions of years ago and scattered its remains through the interstellar medium, where it eventually found its way into the molecular cloud that collapsed to form our solar system, and then into the crust of our planet, and then into the food that became you. You are not separate from the cosmos. You are a temporary and extraordinarily complex arrangement of matter and energy that the cosmos assembled from its own substance over nearly 14 billion years. The void between the stars is not something external to you. It is part of the process that made you. Every atom in your body has crossed interstellar space at least once, and now consider what it means to look up. When you step outside on a clear night and tilt your face toward the sky and let the ancient light of distant stars fall on your eyes, you are participating in something that has no real name in any human language. You are the universe observing itself. You are matter that has organized itself over billions of years and through processes of almost unimaginable complexity into a form capable of receiving information about the rest of the universe and feeling something about it. The stars do not look up at each other. The void does not wonder about itself. The photons crossing the interstellar medium carry no awareness of the journey they are making. But you do. You know what you are looking at. You understand, at least in part, the distances involved, the timescales, the physics, the emptiness. You hold in your mind, however imperfectly, a picture of the cosmos that no other arrangement of matter in the observable universe is known to hold. We are the universe noticing itself. And the noticing, that quiet, irreducible act of awareness and wonder, is not nothing. In a universe this vast and this empty, it may be the rarest and most extraordinary thing there is. I've spent this entire night trying to give you a genuine sense of how far apart the stars are. Not just the numbers, but the weight of them, the emptiness between them, the silence, the cold, the almost perfect nothingness that stretches in every direction beyond the thin and fragile envelope of warmth and air that you are currently breathing. And I hope, in some measure, I have succeeded. I hope the 4.24 light years to Proxima Centauri feels different to you now than it did at the beginning of this journey. I hope the night sky feels deeper and stranger and more honest, more like the actual thing it is, rather than the comfortable ceiling it sometimes pretends to be, because the truth of the cosmos is not comfortable, but it is beautiful, and it is yours if you want it. The next time you look up at the night sky, tomorrow or next week, or on some quiet evening months from now when you step outside and the stars are particularly clear, I want you to remember this. The light reaching your eye has been travelling for years, for centuries, for millions of years in some cases. It has crossed distances so vast that the fastest object humanity has ever built would need longer than all of human civilization to cover even a fraction of them. It has passed through a void so empty it makes our finest vacuums look dense. It has survived the expanding universe, the death of the stars that made it, the passage of geological time, and it has arrived here, in your eye, in this moment, for no reason and every reason, across the beautiful, terrifying, incomprehensible distance between the stars. Thank you for staying with me tonight through all of it. If this journey moves something in you, a like or a subscription means more than you might think. It helps this channel keep reaching curious minds who look up and wonder. Sleep well tonight, and the next time you look up at the night sky, remember the light, and remember how far it came to find you. Good night.